Greetings, grade 12s. This video will go over in two parts the difference between alkenes and alkynes and their relationships to alkanes. So as we get started, a quick recap of what an alkane is. First off, a hydrocarbon is a compound that's made up primarily of hydrogen and carbon. It's the study of molecules that have carbon backbones. There are different types. We've got straight chain hydrocarbons. We've got cyclic hydrocarbons, which form rings or circular shaped structures, and these still have to be saturated with all of their hydrogens. So it takes a long time. We also went over how to draw a line diagram. So for something like this, it would simply be a square where a change in direction of the line represents a carbon. And for something like this first one, it would just be a straight line across. Then we also went over things in branched form. So we've got, for example, here a hexane molecule because there are 6 carbons from left to right. If we start adding molecules, for example, on carbon 3, if we add a branch there, we call this a methyl group. So anytime we see the YL ending, we know that that's a branch off of a longer parent chain. And usually, not usually, always, that has a number that goes in front of it to tell us which carbon of the main parent chain that it's on. There's tons of different types of branching, so be sure to go over the first lesson again. And this one's just going to focus on the different types now. So we'll call alkenes video A and alkynes video B. We'll stop before and start a new recording. So let's get into it. Our goal here is, like with everything so far, to be able to draw, name, and identify the properties of alkenes and alkynes. We're going to see two types of isomers here. So we have geometric isomers, which are made up of the same atoms, just in a different orientation. We also want to describe reactivity of these molecules because once we know what they are and how to draw them, we need to know what they're used for. So we'll start to dive into that as well. So first off, an alkene is a hydrocarbon that contains at least one carbon-carbon double bond. They are also known as unsaturated hydrocarbons, referring to the fact that there could be more hydrogen in them. So they have this general shape. It doesn't mean that they're only 2 carbons long. But we focus just on the double bond at this point. So each carbon in the double bond can have 2 substituents. These, in layman's term, we'll call this things attached. That's what a substituent is. We use the term ligand in terms of when we are learning about Vesper. So this bond is very reactive, and because the double bond likes to get broken, it gives it importance or priority. So when we're naming these, we start the numbering on the side of the molecule where the double bond is closest. So if we've got a chain, let's say here, a hexane chain again, if the double bond is on the first and second carbon, we'll start the numbering from that side. Versus if I have this here, this one's going to be a bit tricky, so we'll just, for argument's sake, start it on that point. If it was on that side, I would call that carbon 1 and that carbon 2. Okay, so it doesn't always get numbered from left to right. It depends where the most important feature of the molecule is, and that priority is based on reactivity. So back to these substituents, if we take the double bond and we kind of draw a plane through it, call this carbon 1 and carbon 2. Each carbon will have 2 substituents on it. So carbon 1 has substituent 1 and substituent 2. Carbon 2 has substituent 3 and substituent 4. This is going to be very important to the shape of the molecule and, again, its properties. So if you've studied any kind of biology and biochemistry, you would have learned about things like trans fatty acids. That comes from the shape of the double bond. So we'll take a little bit of a dive into that and how it impacts the properties of molecules in the body as well. So to name an alkene, very similar to alkanes, only we changed the ending to ene to match this type of molecule. We will have to add some numbering to show where the double bond is. So to do, for an example, if I've got, stick with our hexane molecule, we seem to be comfortable with that, with a double bond here for now. 1, 2, 3, 4, 5, 6. The double bond is clearly closer to the left-hand side. If it was near the middle and I wasn't sure, I would just number it backwards to see which one gives me the lower number. So in this case, if I wanted to name this, it's a 6-carbon chain, so I use the prefix hex. It has a double bond, so I have to use the ene ending, and the ene is on carbon 2, so that has to factor in. So here's how I would write this: hex 2 ene, and this 2 tells me the position of whatever's to the right of it. So that's how we would number this here. If there was branching, for example, we had a chlorine on carbon 4, we'll call that option A. Option B, this simply becomes 4-chloro hex 2-ene, and that's before we talk about isomers, so hang tight on that. One more, if I've got on carbon 4, let's say I've got on carbon 3 a bromine. Okay, we add the substituents to the chain in alphabetical order. So option C here, we would have 3-bromo 4-chloro hex 2-ene. So you can see as it builds, all we're doing is really we're adding chunks. It consists of a number, which tells us the position of the carbon and what's on that positioned carbon. And then towards the right-hand side, the last prefix always tells us what the parent chain is. So the more you get comfortable with this, the more you practice, you will notice that it's the same process each time, but it does take time and exposure. If we've studied hybridization at this point, which we're unlikely to, but if we have gone over it, the carbon double bond has something called pi bonding. This does not allow the carbons to rotate. So you can think of it like a handcuff. If I have two bonds like this and they try to rotate around each other, what they're going to do is get crossed over like two elastic bands, and they're going to unwind. So there is no rotation in these bonds. They're very rigid and they have set shapes. Versus a single bond, if we have this can rotate infinitely without tangling itself up with another orbital. So that has more variation in its shape to it, but the molecules are always arranged in the same order. So because of these molecules are in fixed positions, right? If we have this molecule here versus this molecule where substituent 4 points up rather than substituent 3 on the right-hand side, these are different molecules. They will have different melting and boiling points, different solubilities, and we have to account for that. So everything is still bound to the same carbon, carbon 2, they've just changed direction. So what we use for that is the monomer, the names cis and trans. That'll tell us the direction of the chain and its shape. So we only use those for alkenes. Okay, that's the only time you'll see them, because a triple bond is linear, and you'll see that in the next video. So the way that this works and how we'll use them, when the two highest molecular weight branches are on the same plane of the double bond, we consider that the cis isomer. And you can see it kind of makes this C shape. Now, molecular weight, you can see the note at the bottom, is determined by molar mass on the periodic table. We'll do an example. So whichever chain of the two weighs the most, that is the priority branch, and that's what we're looking at for direction. The trans isomer has the heaviest branches on the opposite side. Okay, so these, you can see this nice shape. These are going to pack nicely, and they'll have pretty high melting points because we can have all of those London forces interacting. So we don't need to know the exact molecular mass, we just need to have a good idea of it. For example, if we know that carbon is 12 and hydrogen is 1, that's good enough. But when it gets more complex, we'll have to be a little more precise. So here's some examples now. We've gone over all the properties of it. If we just looked at naming this without cis and trans, okay, the first thing I'm going to look at is I've got 1, 2, 3, 4, 5 carbons. The double bond is on carbon 2 with this numbering. If I did it the other way, it would be on carbon 3. So this is the lowest one. So I'll make a list here. My longest chain that I like to highlight is right here. So I've got a 5-carbon parent chain, which means my prefix will be pent. On carbon 2, I've got a chlorine group, so I'll just write 2-chloro here, for example. Also on carbon 2, I've got the double bond, so I'll have to note 2-ene in this case. And the last one, carbon 5, even though it's a methyl group, it's part of the main chain. So I don't need to write that out. Because if I wrote it out, I would have to call this butane or butene. But in a row, we have 5 carbons. So that's a longer chain, and that's what we call. So to write this name out, and you'll notice it's the exact same molecule on both sides. So we'll start with this one. The branched substituents go first. So here I've got 2-chloropentatuene. And again, for you to see it, there's the branch, there's the parent chain, and there's a variation of the parent chain. If this was an alkane, we would just have 2-chloropentane. Now, because it's an alkane, we need cis or trans. So what I'm going to do is look at my double bond. I can kind of split it with this down the middle. So on carbon 2, we have a chlorine at position 1, and we've got a methyl at position 2. So from the periodic table, chlorine has a mass of about 35. Carbon and 3 hydrogens have a mass of about 15. So chlorine is our heavier substituent. On carbon 3, okay, I only see 2 carbons going down plus their hydrogen. So I've got 2 carbons, 2 hydrogens here, and 3 hydrogens. So I've got C2H5, which is going to give me a mass of about 29 molecular units. And then here I just have a hydrogen sticking up, even though it's not being shown. So the heavier branch is down. When I look at this, my heaviest branches are above and below. They're on opposite sides of the double bond. So this is the trans isomer. So to rewrite that, I would simply say trans 2-chloropentatuene. And that's our final name here. So again, without the double bonds, we wouldn't have the cis and trans isomers. But the fact that we do means we need to denote the shape, because if this was the other way and that bottom C2H5 group was pointing up, this molecule would pack differently and have different solubility and melting and boiling points. So we can make a note of that if we like. Affects solubility, melting point, boiling point, and to a degree reactivity. Because the bulkier it is, it can block off a reaction site. So let's try this second one. It looks very similar. I can see here that my longest carbon chain looks like this. Okay, I've got carbon 1, 2, 3, 4, and 5 again. So a 5 carbon chain will be pent as the prefix. Carbon 3 this time has a chlorine group on it, and I don't see anything else on it except a double bond at carbon 2. So I can start to put that together. This time I've got 3-chloropentatuene. Now you might think, well, these are very similar molecules. They are, but they will be different in their properties because you have the chlorine so close on this side here. You create some repulsion, and this will affect that the way the molecule can pack itself into a space, and then it's, again, solubility and its melting point. So we draw a imaginary plane through the double bond, and we say, where's the heaviest one? Well, on carbon 2, there's a hydrogen and a CH3. Clearly, it's the CH3. The hydrogen only has a mass of 1 unit. Carbon 3 has the C2H5 group above it and the Cl group below it. So again, from the periodic table, Cl weighs about 35 units by itself. 2 carbons and 5 hydrogens weigh about 29 units. So the Cl is the heavier one. Because the heaviest ones on each carbon are both below the bond, this is the cis isomer. So we would call this cis 3-chloropentatuene. Be sure to go over those examples carefully. Once you understand this, I think the rest of organic chemistry will fall into place for you. The only time we use cis and trans is when there's a double bond in alkene, because we have to take into account that there's no rotation and the shape will affect the properties. So to summarize the properties of alkenes, they are very reactive molecules. A lot of them are used as precursors. This means they're in between steps to make something else. All of the carbons on the double bond, because they are AX3, are trigonal planar. So that's important to know, which means the molecule will always be flat at its double bond. In terms of hybridization, again, if we have gone over that, hybridization just refers to which orbitals overlapped to form this bond. These will be sp2 orbitals. And if we haven't gone over that, then that's something we don't need to worry about here. So the next video will focus on alkynes. We'll make sure we stop here, and we'll call this the end of A. Be sure to review the examples again and continue practicing. This is something that can become very easy in time, but it does require exposure. So good luck.